So now we are proceeding to the next talk, which is by Michael Jordan. So Michael, I read on the web that you begin your studies by cognitive science. And then you proceed to mathematics, and I knew some of your results, which were very theoretical. So you seem to me like a true mathematician. You are a true mathematician, but I didn't know that you were first. And apparently, you closed the loop quite recently, since you were elected as one of the most influential computer scientists. So. I think that we will learn a lot during your talk, and it's a pleasure to introduce you. So, up to you now, Michael.
Okay, thank you very much, Dominique. So let me thank everybody who's participating in this. Let me thank the persistent Pascal Massard, my friend who has tried to organize this now for several years. Here we are, finally. So this is going to be a mathematical talk. By the end of it, I'll be doing things like differential forms and Hamiltonians and maybe even some Malevin calculus. But before we get there, and I hope someone will stop me if there's any kind of audio-visual problem. Seems like I'm okay. Before we get there, I'd like to say a little bit about more on the philosophical level. What is this field that we're all engaging in? So sometimes this field is called machine learning. Sometimes, unfortunately, it's called AI. But what is it? And it's taken me about 3 decades to finally kind of realize what I think it is, because I haven't seen any real new mathematics in the field per se. There's gradient descent, right? And there's diffusions and so on. Not a lot of new mathematics, and especially not a lot of new inferential principles or computational principles per se. So it's borrowing from computer science and statistics, which have hundreds of years of tradition. So what actually is it? Is it new in what sense? So what I actually think it is, finally, is that it's a new engineering field, and it takes decades for an engineering field to emerge and to become mature. So we're really only at the beginning of this. But a point of historical reference would be chemical engineering in the 40s and 50s. Before that era, there was not chemical engineering. It didn't exist as a field. There was certainly chemistry, there was quantum mechanics, there was fluid flows, and also there was actually a deep understanding at the level of electrons and atoms. Of phenomena, but that was in a laboratory. That was with test tubes. The concept that you could build a factory at scale and have fluid flows at massive scale and chemical phenomena at scale, and it would actually work. It would produce product that had to be worked out. So, people tried it. They built factories. Sometimes they worked, sometimes they didn't. Sometimes they exploded, and sometimes they brought value to human society. And little by little, a new field emerged, which is now called chemical engineering. Now, I want to emphasize it's not just engineering, quote unquote. It has its own mathematics. There's new principles of thermodynamics at scale and fluids and so on. So it's a highly mathematical field with new ideas, but it took a long time for those to develop. And fundamentally, it was about building things in the real world. I think that's what's happened here, is that we had the principles of statistics, inferential, we had computational principles, and it got put together in a way that started to solve real world problems. But it's not really solving a lot of real world problems yet, and it's causing some headaches and some problems. So we don't have the engineering field yet to support building real world systems, but we're working on it. And new mathematics will emerge, but I just don't think it's yet emerged, but we're probably going to see it certainly within our lifetimes. Electrical engineering, I know less about the history, but I think it's pretty similar. You had Maxwell's equations, so in some sense you had everything. But the idea of building circuits or bringing power across the country or lighting up a city, that required new ideas and new mathematics, in fact, and that's what you study when you study electrical engineering. It's not, quote unquote, just engineering. Okay, so that's my perspective. Now, if we're going to think at that level about this new emerging engineering discipline, it can't be just pattern recognition. It can't be just neural nets trained with large amounts of data. Okay, if it's going to work in the real world, you got to think about other problems, in particular decision making. And I want to emphasize that I think decision making is equally important to pattern recognition. Can't have one without the other. And in particular, when we talk about high stakes decisions or planetary scale networked decisions, not just by individual agents. I think the AI terminology has made us focus too much on individual agents. But if you think about networks of flows of data and value and decisions, then you start thinking the right way about this new emerging engineering field. and particularly you start to bring in economics ideas and dynamical systems for economics. All right, so if this is a reasonable perspective, it shouldn't be just in academia that we're talking about. It should have been in the real world. It should have happened already, and I believe it has. So here's my history of machine learning, fairly different from most people's. But I think in the first generation, it was already in the 1990s. You had companies like Amazon.com building large backends, many computers, thousands of servers, the origins of the cloud, to do things like supply chain management and fraud detection, to make e-commerce actually possible. And they were using random forests and probably a little bit even of neural nets in the day. And so things haven't really changed that much. Large amounts of computers, large amounts of data, and gradient-based algorithms. They were already doing that, and they built $1 billion industry on that. So has anything changed? Well, yeah. The second generation, I think people realized a lot of the data was about humans. So recommendation systems emerged. Now it's more about preferences and decisions and less about just modeling ships moving across the ocean. All right. I think the third generation is what I'm calling the pattern recognition generation. It's the deep learning era. It's because a lot of the data is not now just from humans. It's really about humans. It's about their speech patterns, their visual capabilities, their language capabilities. And so you apply the same technology, gradient algorithms, large scale data, and it's at a bigger scale. So it's working even better, and it looks human-like because it's doing things that imitate humans. And so the AI terminology or buzzword, I think, came back in that era. And again, I think that's unfortunate because I think that's limited the scope of our thinking and our research. Because I think in the meantime, we've seen the emergence of a whole new era, which I think is the era of markets. So think about the response to the COVID outbreak. It's a planetary scale flow of data at small scale and large scale about what works, what doesn't, logistics chains, treatments, analysis of sequences, and so on and so forth. Very ad hoc, but it is in some sense a decision-making system. The planetary scale for a system for commerce or for transportation or for finance are very similar. They're blends of humans and machines and decisions and values and so on and so forth. So it's kind of a big stochastic control system, if you will, that has a lot of learning in it, but it's very ad hoc. And so we've got new challenges to try to make systems like that less ad hoc and more understandable. I'm going to skip over my outline because it's actually changed as I've been preparing the talk. So let me emphasize this issue about decisions, why it's not just prediction. So I don't agree with a perspective that says that prediction is sort of everything. If you can predict well, you're done. Imagine that you go into the doctor's office next year, and they measure all kinds of things about your body. They take your genome, they measure thousands of variables of 100,000 dimensional feature vector. That's been trained on all the world's medical knowledge. Imagine that goes into the world's largest neural net. It's been possible. All right. And so now is that training set and test set. Yeah, so you walk in the doctor's offices, they sit you down, and out comes a set of predictions. And so like one of the output units says, I'm the heart attack predictor. And it says, if the value is over 0.7, I'm going to predict that you're going to have a heart attack soon. You better do something. And suppose your value is 0.701. Doctor tells you that, what are you going to say? You're going to say, well, okay, obviously I'm going to have a heart attack. It's a very good prediction. No, you're going to have a dialogue with the doctor. You're going to first of all say, what are the error bars on that 0.701? And error bars, I don't just mean Gaussian asymptotic error bars. I mean, what is the source of error here? Is the data recent data, or is it data from 10 years ago? Is it data about people like me? Is it data on the same kind of machines that were used to assay me? Is it relevant to my situation? And moreover, I'm going to start thinking about things about myself that I hadn't thought about before. Like, oh, I remember that I had asthma when I was a kid, or I'm going to also do what if questions. What if I were to exercise more? What if we got a different opinion, and so on? We're going to have a whole dialogue, and there'll be counterfactuals in that dialogue, that things that weren't in the data, or things that I remember that couldn't have been in the data. And that's going to happen for every kind of real world decision making. Consequential decisions involve thinking about new facts that were never put in the original data that are relevant to the current situation. And it's going to be a dialogue with counterfactuals, adding new data, rerunning some analysis, and so on and so forth. All right, that's what real decision is when it's consequential, like life and death. All right. Now, it's not just one decision generally. I'm making lots of decisions today at different time and spatial scales. And I really want to have control over errors on all of them. And I'm going to have they're going to interact in various ways. And now it's not just across my lifetime today, it's across a network with other people making decisions that interact with mine. It's also across multiple time scales. You know, there's decisions in this current hour, but there's decisions over several years that I'm currently kind of making. So this idea that you collect a big training data set and you train it and you kind of have predictions for today, I think it's pretty far off the mark. Moreover, there's going to be asynchrony, there's going to be then scarcity and competition, because real decisions in the real world have to do with entities that can't necessarily be replicated, where there can be congestion and there can be competition and scarcity. So that starts to bring in the economics perspective. So as a thought experiment, let's consider a recommendation system, the kind that might recommend you should have heart treatment. It's become a commodity. It's a pattern recognition system that sees patterns in historical data and makes predictions. And it's often treated as a decision-making system, but it really shouldn't be treated that way. So let's think about it helping us in various domains. If it's recommending movies to people, and many people start to use the service, like millions, it could easily start to recommend the same movie to 10,000 people or 100,000, and that's not a problem because there's no scarcity in the world of movies. You can copy the bits as much as you want. Same thing with books. But if you start recommending real-world goods like restaurant seats, you could, again, if everyone's using your recommendation system, you could recommend the same restaurant to 10,000 people in a given city. If everyone in the city is using the app. And now what do you do at that moment? You've created a congestion. You could imagine that your job as a computer scientist is to do the load balancing. You want to figure out what people really want and then allocate the right people to the right restaurant. And that's kind of what advertising systems attempt to do. That's what the Silicon Valley attempts to do, is figure out so much about us that they can make really good predictions, and therefore we'll all be happy. And I just think that that's almost a farce. It's just wrong. That's not how humans make decisions. We really want to be in a little market, and on one side of the market are me and other diners, maybe millions of us. On the other side of the market are maybe millions of restaurants, and there's going to be a matching and bids going back and forth and valuation, and there's going to be exploration, exploitation, and so learning meets economics in some kind of a grand market kind of system. That's the right way to think about the machine learning problem. It's not just collect old historical data, make predictions, and then hand it over to somebody else. If you start recommending streets, it's well known already that creates problems. You'll create congestion by sending too many people down the same street. You have to match again, and you don't want to you figure out how to send people down streets. Recommend the same stock purchase to tens of thousands of people, you'll destabilize the market, and so on and so forth. It's easy to think of examples, and I hope you now appreciate that decision making is very much its own thing, not just pattern recognition. All right. So the alternative, I think, is kind of clear at this point, is that you don't just create a prediction system, you created a market, and it's going to be maybe a multi-way market. Consumers on one side, producers on the other. They're both learning about the effect of their actions in the context of other decision makers. So this is not just classical microeconomics. You're saying let's bring a little bit of game theory or matching markets into machine learning, because in that literature, you assumed that you knew the preferences a priori. Each agent would write down on a list, which college I want to attend, and they would know that preference list a priori. The colleges would write down which people I want to accept, and then there would be a matching algorithm run on that data. It's not data, it's assumed to be known a priori, or maybe there's a Bayesian prior. That's the economics literature, and that's not sufficient, because in the real world, I need to experience the restaurants. I need to experience what the effect of the options are, and my taste may change, and there's an evolution. So learning is critical to building really good future economic systems. I just want to mention David Blackwell. My perspective that's kind of emerged over the last few years is, I have many predecessors in this, but particularly David Blackwell, who I got to know when I first arrived at Berkeley. He blended statistics, economics, probability, and algorithms, and this perspective in some sense is really nothing new. David would have definitely said many of the same things I'm saying. Unfortunately, he was rare, and if you look at the links between statistics and economics, it's mainly just kind of time series analysis and some causal analysis. It's econometrics. And if you look at computer science meets statistics, it's kind of machine learning, but there's not much economics. And then economics meets computer science, I guess I'd call that algorithmic game theory, but there's very little statistics in that, so there's some in all these cases, but there's not a realization that there's really a complete need to blend these things in the way that David Blackwell did. People have recognized that markets can be viewed as algorithms. They're decentralized, they do complex tasks. It's not like an AI agent, it's a system that works, and each little node can be kind of stupid. And it can be at planetary scale. It's based on auctions and bids and so on. It can work over long lifetimes. It's pretty different from our current machine learning systems. And so the idea of blending our current machine learning systems with markets as algorithms, I think, is the right way to think about the future for our field. So there's lots of new problems here. I'll turn now a little bit more to the kind of mathematics. If you start talking about exploration, exploitation, multi-world markets, we'll mention something about that. Talking about information sharing, how does that stabilize and allow you to develop new learning-based markets? Auctions, when you actually learn the preferences, not just assume they're known, and so on and so forth. So we want to build we need new principles, new mathematics that allows us to build learning-based markets that are stabilized over long stretches of time. All right, so let's now go to a very specific example. This is one of the early pieces of work I've done at Berkeley with my students Lydia Liu and Horia Mania. We're going to bring together my favorite learning algorithm, which is a multi-arm bandit, with matching markets, which is my favorite piece of microeconomics. Okay, so you all presumably know what a multi-arm bandit is. You have an agent has several actions. They get a reward associated with each action, and they don't know the reward distribution a priori. They have to try things out. So this is pretty different from supervised learning, where you're sort of told the right answer, and it's different from unsupervised learning, where you aren't told any sense the right answer. Here is somewhat a little bit in the middle, and I think the middle is often a very good place to be. All right, so you try out actions here, and you get a reward back, and actually I should have had a slide there, right? This slide. So there's an algorithm that is very famous, the UCB algorithm, which takes these rewards, and it doesn't just build like an estimate of the mean reward for each arm, even though that's what you're trying to optimize. It builds a confidence interval for that value for the mean reward. And why do you build a confidence interval? It's not just to be a good statistician. It's really, if you're going to do exploration as well as exploitation, you need to have a confidence interval. So the upper bound of the confidence interval encodes two ideas. If it's high, it might be because the overall reward distribution shifted up, over to the right. So that's good. You should pick that arm to exploit. But it might be high because you have a lot of uncertainty about that arm. So you should pick that arm to do more exploration and decide whether it really is a good arm or not. So anyway, that's the UCB algorithm. Okay, so on the economic side, let's look at matching markets. Hopefully you all also know what these are. We have buyers on one side, sellers on the other. The buyers have a ranking for each of the sellers, their preference list, and the sellers have a ranking for each of the buyers. And then there are algorithms, for example, the famous Gale-Shapley algorithm, which will match things and has a property that it gives you a stable match, that no one buyer and one seller would like to swap with another buyer and seller to improve their own lot in life. All right, so what if we put these together? What if we now have a market in which we have multiple agents and they're both trying to figure out what's the best actions, the best rewards, all right? But they're competing, meaning that if they both happen to pick the same arm on a given trial, so here the bear and the human have both picked arm 2, only one of them gets a reward, the other gets a 0. Okay, or not a 0. The other one gets a no reward. Let's call it no reward. Now, which one gets the reward? Well, we made a modeling choice, which is that we said, look, the arms have preferences back on the agents, and they may be learning those preferences too. But in any case, they have unknown preferences. But so we've learned here, the bear has learned that if I pick arm 2, I will maybe get the arm, and the human has learned I may not get the arm. So the human now says, okay, I like arm 2, but I see the bear likes it as well. There's competition. I should probably explore some of the other arms that I wouldn't have otherwise explored, and have some hope of getting a high reward. So there will be a penalty, and I'll do worse in terms of the regret because I have to explore more than I otherwise would. And the question mathematically is how much worse. So as you may know, the UCB algorithm has logarithmic regret as a function of the amount of trials, the number of experiences you've had. It's logarithmic relative to an oracle that knew the best arm a priori. So that's really good. Logarithmic is excellent. Can we still achieve that, or are we getting a penalty that makes it worse than logarithmic? All right, so we have this bandit market, agents on one side, arms on the other. It's an exploration exploitation situation. That's what we're calling a bandit market. And we define the notion of regret. I don't want to spend too much time on details here, but it's kind of an obvious notion. It's imagine there's an oracle which is running the Gale-Shapley algorithm on known preferences, known a priori. That's our oracle, and we want to say how well do we do relative to that. All right. And so the algorithm we first analyzed, we've now analyzed a bunch of others. We called just it's a blend of Gale-Shapley and UCB, Gale-Shapley upper confidence bounds. What you do is each agent maintains a confidence interval on the rewards for each arm, and they send the upper confidence bound to a Gale-Shapley algorithm, which makes the matching based on that, and then you get to get a reward from the arm that you're matched to. Okay, so notice it's not a it's a centralized paradigm in this particular algorithm. We've followed this up with other work which I like a little better, which is decentralized. But anyway, this is a very clean, simple algorithm, and you can analyze it, which we did, and we found out that it in fact still has logarithmic regret. So here's the regret bound. It's logarithmic in the number of trials in, and in the denominator there is a term delta squared, which is a reward gap. We're used to reward gaps between the different arms for a single agent. This is actually richer. It's the rewards between different agents for the same arms, right? So if Pascal is also in the game with me and I'm playing it, and he and I have same preferences over the arms or similar, we have a very small reward gap, and so that denominator will be big, and I will pay a constant penalty in my regret. It'll still be logarithmic, but it'll be worse. Because of the presence of Pascal in the game, if he has a high overlap with his preferences with me. All right, so you can go in lots of directions with this, and there has been already some little follow-up literature. There's lots more to do. The decentralized paradigm, the paradigm where there's many, many agents, like millions of agents or millions of arms, so you can't experience all of them, but you share information with some of the other players in the game, and so on and so forth. So there's just a whole rich set of work to be done in this kind of field. That's just a simple merging of game theory with machine learning. Just as a little bit of dessert here, having gotten that kind of result, we started applying UCB procedures to other decision-making problems. I like agents that are learning via multi-arm bandit, or contextual bandits is another favorite, but also there's reinforcement learning where you have a sequence of decisions, not just a single decision at a time. And so this is the optimal control problem. So with Shijen, Zayad Anjou, and Sebastian Bubek, we simply asked what happens when you bring Q-learning into register with UCB. All right, so no details here. I just want to quickly mention this result. You all know that reinforcement learning is kind of like the bandit problem, but you have states, you have action states and rewards. So there's a transition distribution. There's a big argument whether you should learn the transition distribution, that's the model-based paradigm, and then optimize based on the learned distribution. That's kind of what an optimal control perspective would lead you to do. Or you simply go directly for trying to find this best, exploring in the space of policies or actions. That's the model-free paradigm, and it's closer to the bandit style. Now, even though this kind of is viewed as originating from the bandit literature, it sort of at some point threw away the exploration exploitation trade-off. It just kind of went for exploitation pure, and exploration just kind of came in as random, throw in a random action from time to time, epsilon greedy. But really the real problem should be exploration, exploitation, and learning sequences together. All right, so here is an example of an algorithm that does that. And again, details I'm not going to get into here, but if you know Q-learning, this is just the Q-learning algorithm. It's just dynamic programming. And we've added a UCB penalty. That red B sub t there is a upper confidence bound that we've added to the Q value prediction. And it scales in a certain way. You can see that at the bottom of the page. We now have an algorithm we can analyze in terms of its regret, not merely its expected reward over time, its regret. All right, so we did that. And then on this last page, there's a lot of detail here, but this is the state of the theory of reinforcement learning when there's exploration exploitation. It's now a little bit out of date, this slide. There's been now some new developments, but basically there's a comparison here between model-based on the top and model-free. The model-based work at the top, you see a bunch of algorithms. They were all able to show square root of t regret. T is the number of time steps. right? So that's good. It's not logarithmic, you know, but it's square root of t, which is still effective learning. If you go to the bottom part, the first two lines there are Q learning with epsilon greedy, and you can see the regret is not square root of t, it's t. It's terrible. All right. There's another algorithm which got it down to t to the 4/5, but it still looked worse than the model-based paradigm. All right. But what we were able to show in this paper is that if you put in a good algorithm for exploration, UCB in particular, and you blend that with Q learning, then you actually get square root of t regret for the model-free paradigm. All right, so this kind of puts the two paradigms on the same footing. They really do have the same kind of regret performance when you really take the exploration seriously. Okay, so that was just a little bit of work on sequences of decisions. Right now, when you talk about decision making, it's not just one decision at a time. It's not just sequences. It's often bags of decisions, collections of decisions, perhaps made by multiple agents or single agents, and they're often asynchronous. So this is a line of work, several papers with Tiana Zernich, a student of mine at Berkeley, and Aditya Ramdas, who was a postdoc with me, who's now a professor at CMU. And I just want to, again, kind of highlight a few results here. We have a whole bunch of papers on this, but I want to highlight kind of a couple of the take-home messages. So first of all here, you would like to be able to make decisions over a lifetime, okay? Meaning that as I go through my lifetime, I have a certain probability of making an error. All right, and the naive perspective is just that probability accumulates over time, and the probability I'm making an error goes, you know, beyond 1, and I kind of have to stop if I wanted to have control over my error rates. But that's not how humans think about life. We don't think about, you know, the accumulated error so far, and so we got to develop a paradigm that allows people to continue to make decisions and kind of measure errors in the right way. All right, so there's going to be an economic metaphor here. We're going to kind of accumulate wealth and spend it. And we're going to do that in a way that there's kind of a error metric, which is actually under control. All right, so on this slide, kind of, I'm going to set up the FDR criterion. And hopefully you already know what FDR is. But here we're not making just one decision, we're making 9 decisions. The gray ones on the left are represented by p-values, but however you want to represent them is fine with me. There are 5 decisions there where you should say null. You should say there's no discovery to be made. Okay, you accept the null hypothesis. And there are 4 on the right where you should say non-null. You're making a discovery. You think there's something really happening for that particular decision problem. Okay, and let's suppose here that you run some algorithm and it makes the discoveries are in red. There are 4 discoveries that have been made, but 2 of them are false. So your false discovery proportion is 2 out of 4. That's pretty bad. And then we want to analyze the expectation of that to be statisticians and get an actual error rate. That's called the FDR. Okay, so sadly, this should have gone one slide at a time, and I should have gone through this. You've got the whole slide all at once here. So let me just walk through sequentially a little bit. So let's imagine, what I want to get on this slide is the big difference between error metrics like accuracy and sensitivity, specificity, the kind of things we're used to in machine learning, and these FDR or FDP kind of metrics, which I think are often the better way to think about the problem. You know, not always, but often. So imagine you're running 10,000 different A/B tests today. You know, you're like Amazon or Google, and you're trying to change your website or change some protocol. So you're doing a lot of A/B tests, and you hired some employee to do this. You gave them a few $1 million, and they did it in a nice way. They ran each one of them independently, different people, so and so on. But as in most problems, we're in a mature industry or mature science, most of the tests should come out null because there's nothing left to discovery in a mature system. Or if you change the website a little bit, it's not going to be worth it to actually implement that change. So let's suppose that 9,900 of these actual tests, you should say null. Don't bother to make a change. It's not a good idea, or it's not a discovery. Whereas only in 100 cases, there's a discovery to be made, okay? And let's imagine you run a really good classification system, the world's best neural net on this kind of problem, this kind of data. And suppose the type 1 error rate, the false positive rate, or 1 minus that, is 0.05, okay? So, sorry, the false positive rate is 0.05. All right, so if I run that on the 9,900 true nulls, 0.05 times 9,900 is 495. So I made 495 false discoveries out of 9,900 true nulls. A very good, accuracy, obviously. Now, the same neural net is going to be also applied to the non-nulls, and let's suppose my power, my sensitivity, is 80%, so maybe not so good, but pretty good. And so 80 times out of 100, I make a discovery when I should. All right, so I have a really good sensitivity and specificity, right? But the problem is I don't have a good actual error rate, and in the sense that it really matters. Suppose that a boss comes in at the end of the day and they say, how many discoveries have you made? I gave you a lot of money to run 10,000 tests. And you say, well, I made 495 plus 80. I made 575 discoveries. And the boss says, okay, I'll take those and I'll implement them and hopefully we'll make a lot of money on them. The problem is that the Oracle knows that actually 495 of those were false. So your fraction of false discoveries is 495 out of 575. You did a terrible job. And the boss then a few months later will figure that out and you'll get fired. All right, so this happens all the time, and it's just naive usage of kind of decision theory, if you will. And so really the message is we should be not controlling sensitivity specificity necessarily, or squared error or whatever. We should be controlling more things like the FDP. The classical approach to this in statistics doesn't seem that relevant to machine learning because it's a very batch-oriented procedure. You collect all of your test statistics, your p-values or whatever, you batch them together, you sort them, and then you do a threshold based on the sorted p-values. Very definitely not an online procedure, but also it's not an anytime procedure. All right, by that I mean that I should be able to have the boss come in anytime during the day and say, how many discoveries have you made up until now? And I say, 35. And they say, well, what fraction of those are false discoveries? And I say, 2. It's less than 5%, I can guarantee you. And they come in a few years later and they say, how many discoveries have you made up until now? I say 4,000. They say, what fraction of those are false discoveries? I say, well, only 17. Again, less than 5%. And that should be able to be happening throughout your lifetime. All right, now is that even a meaningful thing to ask for? Is that too much? And the answer is no, because FDP, if I go back here, is a ratio. And both the numerator and the denominator are random variables depending on the data. That's what's unusual about this criterion. So I can make this ratio small by making either the numerator small or the denominator large or both. All right, so the numerator small is just keeping the false positive rate down. We're used to that. But also doing that while making the denominator large, we're not so used to that. All right, and so a number of people, including our group, have worked on this. The original paper was Foster and Stein, statisticians at Penn, Dean Foster, and there's also a very nice work by Javanard and Montanari at Stanford. Our version of this is called Saffron, and basically it's just a way of making sure the denominator gets large at the same time that the numerator is under control. And it's just a specific algorithm that whenever you make a decision, it just adjusts some parameters so that happens. And there's a kind of a simple little martingale proof that sort of assures you that this works. Actually, it's not even a martingale proof. The beauty of the online setting is you actually don't even need very much mathematics. It's really a very kind of empirical Bayes simple argument that shows you that you're controlling this. And so kind of conceptually, it's kind of got an economic story. I give you a certain amount of wealth in the beginning of your life, like 5%. And every time you do a hypothesis test and you don't make a discovery, you lose a little bit of your wealth. And then when you make a discovery, I give you a little bit of extra wealth that you can invest for the future. And so this is how humans would naturally operate. If they're not making any discoveries, they realize that they're kind of working in the wrong field. They change fields, or they're working on the wrong problem, so they change the problem. And they start making now some discoveries, and now they are allowed to keep going. And that's what this algorithm does. Okay, last few minutes, or 5, what have I got? I think, let's see, 45. Started 10 minutes. Well, I think I may have up to 10 minutes, but tell me if that's not true.
Right.
Okay, so now what's the mathematical machinery underlying a lot of these kind of problems? Well, these are all dynamical systems. They're all in a high dimensional parameter spaces. There's stochasticity and so on. So we got to start to develop the right mathematics for problems like this. I'm just going to say I don't think we've developed any new mathematics here, but we've really more deeply used the toolbox of classical mathematics. And we're going to go symplectic and variational and Hamiltonian. We're going to try to go for optimality principles. We're going to ask not just what's a good algorithm and what's its convergence rate, but what is the best algorithm? What algorithm diffuses most quickly to the stationary distribution? Or what optimization algorithm goes most quickly to an epsilon neighborhood of a stationary point? How do you get past saddle points optimally? So on and so forth. So those optimal problems is kind of the optimal way to optimize or the optimal way to diffuse. We really now need variational Lagrangian or Hamiltonian type perspectives. So this work kind of originated with a paper that I had with Andre Wibissono over there, who's now at Yale, and Aisha Wilson, who's now at MIT, and then Mike Betancourt helped us a bit getting going on the symplectic ideas. All right, so this will go kind of somewhat quickly. It's a little bit older line of work, but it really does helpfully bring in some of the mathematicians to help us with some of our emerging dynamics problems. And I just want to make another philosophical remark, which is that in mature fields, there's a lot of interplay between differentiation and integration. You go back and forth between the two perspectives all the time. Certainly physics has it for sure, but statistics does too, and the numerical disciplines like finite elements and analysis have it. Optimization almost has no integration in it. It's almost all just derivatives, Hessians, gradients, and so on. And the idea that there should be an integration perspective is not that common. So that's what we're really trying to bring to this. So I think you saw a talk by Francis Bach earlier today, a world expert on optimization, convex and non-convex, and you've seen things like here's gradient descent at the top of the page, here's an Nesterov acceleration, which is a second order algorithm at the bottom of the page, and you get the convergence rates, you know, in a smooth problem of 1 over k versus 1 over k squared. Triggered by some beautiful work by Weiji Su and Emmanuel Candes and Stephen Boyd on looking at Nesterov acceleration as a second order differential equation, we started looking at second order differential equations for a range of algorithms, including the accelerated ones, asking what properties they had. And long story short, we found a Lagrangian, which in continuous time gave us all of those algorithms, all the ones we knew at least. And again, I'm definitely not going to get into details here. There's a lot of papers on this, but here's our Lagrangian. It has a Bregman divergence at the top. It's kind of a dynamical Bregman divergence, if you will. It's between x, which is your current position in some configuration space, and x plus a time-scaled x dot. So it has a kind of a elasticity flavor. And then you subtract off a time-scaled version of the optimization functional. So it's like a potential energy. So in fact, this is kind of like a kinetic minus a potential energy. It's a time-varying Lagrangian. All right. So if you just do variational calculus, at the bottom you'll get out a master differential equation, which has in it the Nesterov or the Su-Boyd-Candes algorithm and many other accelerated algorithms in continuous time are given by that equation at the bottom of the page for particular choices of all these degrees of freedom, alpha, beta, gamma, and so on, and the geometry given by H. All right. We were then able to analyze this and shows it has some differential geometry properties. It's covariant, so you actually follow the same flows, different speeds. We got the convergence rate once and for all, and so on and so forth. Right. But the real interesting mystery became that we found in continuous time, you can flow as fast as you want. You can go exponentially fast and solve optimization problems. But we know in discrete time, because of these oracle results by Nemirovsky, you want. There are lower bounds, like 1 over k squared and others, that you can't go as fast as you lowered and so on. So there's a time, but it's sort of figured out you go as fast as you want and continue, not in discrete time. And we set out eventually. There's a phase. So we like to find that phase transition and characterize it. And long story short there, it turns out that symplectic integration ideas allowed us to find that phase transition and characterize it. If you don't know what symplectic integration is, it's goes back to Hamilton, Jacobi, and others, Poincaré. Instead of thinking about a vector field as that I integrate a vector field by arriving at a point in my configuration space, looking at the vector, leaving that point, and following that for a little bit. Instead, I think of a triple of vectors at each point, and as I flow along the dynamical system, that triple will shear, and I'd like to keep its volume constant. All right, so that's a very stable way to think about integrating differential equations.
I will have to cut you a little bit because we are running out of time, and the connection, besides the connection, is a bit difficult. So sometimes we.
I see. Okay. Well, I was going to finish in 1 minute. I just wanted to finish this one point.
Yeah.
And let me do that. So I'm sorry about the connection.
No.
Okay. So please, yes.
Yes, yes. Go on.
Okay,
Just a point, and then we pass to the question because there's several questions.
okay, okay, very good. So just to say that symplectic approach compares favorably to Nesterov. It actually goes faster when you turn up the step size. And then the last point I wanted to make in my last 1 minute, and I think I'll have to skip through a couple of slides to do this. I'm going to skip through this, which is that if you go to the problem of now finding Nash equilibria in games, this is a gradient ascent problem. And we have worked on the zero-sum game problem where you're going up in one direction and down in the other, trying to find the saddle points. And long story short, these standard algorithms of gradient-based methods don't work here, that they will oscillate, arrive at limit cycles, and so on. And there is a way to solve this problem by canceling the symplectic component. So again, the symplectic component of these dynamical systems turns out to be efficiently computable and appropriate for learning problems. You either exploit it in the optimization setting or you cancel it in the game theoretic dynamic setting. Okay, so that's all I wanted to say. That shows this algorithm works. And this slide I already had up before, just emphasizing again, pattern recognition, decision making, two sides of this overall field. They both are important. They both require mathematics, and they're going to require new mathematics going forward. So hopefully I gave you a little bit of inspiration and flavor of what that mathematics might start to look like. Thank you very much.
So we thank you very much for this very inspiring talk with a lot of direction. And so I will pass to some questions. There is several questions in very different direction. So I will proceed with one of the first one, which were what is the accountability of artificial intelligence supported decision-making process in the public sector? Do you have answers to that?
The accountability?
Yeah.
So I'm not really sure what that means. Maybe if that person can come back and say again. I mean, accountability is sort of the whole point of this engineering field, is that we should be accountable to to real people, just like people that built other engineering artifacts like chemical engineering. You know, it made things that brought value to people. But we've got to talk about that value in economic terms, meaning individual humans, what their utility, a society. When we talk about things like fairness and privacy, those have economic content to them, and they reflect my own utility. Being treated fairly has to do with being treated not the same as everybody else, but being treated in a way that matches my utility and respecting my utility. So maybe that sort of helps a little bit to give a flavor. For me, thinking about social welfare and thinking about how learning interacts with society and with individual humans, requires adaptivity, and it also requires economic value to be understood and be brought into the picture. And so accountability to me, as the word, has a flavor of also kind of auditability and guarantees. And it's like when you brought electricity into your home, 100 years ago, could you guarantee that home wouldn't burn down? Well, there was, underwriters' laboratories that came in and would certify that it wouldn't. They give you certain guarantees, and those kind of things are needed for our field as well, auditability and so on and so forth. So it's it could be a long-winded answer, but let me just stop there.
Okay, thank you. Anyway, also I have another question about interpretability. So when it says when human makes decisions, they need interpretability, but current deep learning lacks of interpretability. So will deep learning be in the future of machine learning era decision making?
Yeah, no, it certainly will. It's just deep learning, and maybe the narrowest version. It's regression, right? It's high dimensional nonlinear regression, and you'll always need that. We always needed it. We always will. But go back to my medical example with the doctor. We're using the deep learning model there to help make some predictions about what your health status is, and hopefully that'll orient our decision-making process. But the decision-making process is all about interpreting that prediction. It's about saying, well, what's the context exactly of that prediction? What data was used for that? What's the provenance of the data? What's the reliability? What other things could be done? It's reanalyzing the data from a different perspective, et cetera, et cetera. So you get the interpretability not just by looking at the artifact of the neural net, You get it by putting it in a whole decision-making process, which involves counterfactuals and reasoning and probing and rethinking the problem. And in that process, the interpretability starts to arise. It's just like a doctor. A doctor for me is often a black box. They have this knowledge I don't know how to access. But as we talk about a particular medical outcome, me and the doctor will start to develop trust with each other, and information will start to flow. And I will interpret their assessment that I have some problem. So it cannot be thought of as let's find the features that most predict the output, or let's turn the neural network into a decision tree or something. That's just such a narrow perspective on what's really a very important problem of giving people confidence in the whole decision-making process and not just the output of a machine learning prediction box.
Okay, thanks. Now let's turn to maybe a more technical question, which refers to another talk. So the question is the following. Francis Bach said that reinforcement learning can be seen as an instance of control theory, but it seems that there is no pure control theory without reinforcement learning for multi-armed bandits, meaning that there is a few exceptions within reinforcement learning that are not control theory. Is this true? So this is a very precise and technical question.
Okay, so I don't agree with it. No, it's not true. But also, I don't like this kind of artificial distinctions. I mean, I could make models of the world. That's often called the plant, and have them be good models, adapt them over time one way or another, maybe with data, maybe with expertise, and then build stabilizing control loops and trajectory following things, and doing that at any scale that's needed. And if you say, Mr. Control Theorist, you're not allowed to use the multi-arm bandit procedure to help kind of explore, they're going to say, what are you talking about? That's part of my discipline. It's part of my field. And so reinforcement learning, unfortunately, it's this AI hype thing, that everyone says it's brand new and it solves the world's problems. It's really a search algorithm. It's stochastic version of optimal control. Ideally it does some exploration as well. But it's really just a particular algorithm for doing stochastic optimal control. And bandits is one aspect of that focuses mostly on the exploration. But it's all kind of one big integrated picture. To me, the superordinate nodes in a lot of this is statistics, where you're talking about decision making under uncertainty, and how do I gather data, and how do I look at the population, and then control theory, where I'm trying to think about what if I do this in the real world, will something actually change and move? So I'll need, for example, causal inference to do control theory. So those fields, which like in the 30s you had Wiener and Kolmogorov and all, they focused on that, and they focused on probabilities to allow, and dynamical systems. That to me are kind of superordinate. And in machine learning, we're way down in the weeds. Reinforcement learning is one particular Monte Carlo class of techniques for doing Bellman equation. So it's not one of the big superordinate nodes, reinforcement learning. So if that's the content of the question, I totally agree with Francis Bach. No surprise when he sort of starts to put these things in the framework of control theory. I totally agree.
Okay, I think we will stop the question there because we are running out of time.